Thank you. Thanks for the introduction, and thanks for the invitation to speak in this beautiful city, in this institute surrounded by mountains. So I'm going to talk about a little project of mine concerning Quandles and Profinite rigidity. I will explain what that means, and I will first give a gentle introduction to Quandles and how they're used to color knots and links. Then I will give a picture of the big context and explain where my contribution sits in there. And then I will explain a bit what that is. So let's begin with an introduction to Quandles. So these are little algebraic structures. Introduced in knot theory. They had appeared before, but independently by two mathematicians, Joyce and Matveev, very independently because they were on both sides of the Iron Curtain. In 1982, the goal was to color knot diagrams. And a very notable result, which is proved by both, is that there is kind of you can color knots by Quandles, by elements of a Quandle, and there is a universal Quandle doing that, which is called the so K is a knot. And this is a complete invariant of knots, or up to taking mirror images. And so why is that? That's because actually this is a nice way to encode what is called the peripheral system. And the fact that this is a complete invariant, this relies on work by Waldhausen on Haken manifolds in the 60s, I think 68. Yeah. Okay, so let's explain now in detail what a Quandle is and how we color knots of this. So what we want is to color knots, knot diagrams, knot and link diagrams. I'll talk about links later. With some colors, and colors will be elements of a set Q, and we impose some coloring rules, and the rules are as follows. If I have A and B like this, then this one, we color arcs of the diagram, and this one will be colored by something depending on A and B. My knots and links are oriented. And since they are oriented, there is another type of crossing. And if I have something like that, then here I have something, another thing depending on A and B. And so what I need here, so here this stays the same, and here too. So what I need is two laws from taking two elements of Q, two colors, and giving a third one. And I will ask for this. And then I have a diagram, and I have an isotopic diagram. Then I want to have a bijection between colorings of the first diagram and colorings of the second diagrams. So if I have a coloring of the first one, I want a coloring of the second one. And so to have this, I want to have some compatibility with isotopies, that is with Reidemeister moves. So the first thing is that if I have something like this, so this is one arc without, which is not cut, so it's the same color, then I want to deform it like this. And outside of the deformation, I want to keep A. But here, if I follow my rule here, here is A, and then it's this one. So I want this to be equal to this one. That will be my first axiom. The second one is Reidemeister 2. So if I have this, like this, and I want to deform it into this. So what do I get here? I get A acting on B, and here I have another crossing, a crossing of the other type, and then I have this and A. So I want these ones to be equal, and the converse move. So what I want actually is that this one should be the inverse bijection of this one. So actually I have only one law. The second law is just taking the inverse, and so I will call it just with an inverse like this. Okay, and now we have Reidemeister 3, so let's do a picture. This, and then this one goes there, and this one goes there. Okay, so here A is staying the same. B will stay the same until then there, and then we get A over B. And here it passes, B passes over C from the right, so we have this picture, this, and then here we get this thing. On the other hand, here we have A, B is getting under A, so we get this, and here it passes under A, and then it passes under this one, so we get, let's get there, this, and I want these to be equal. So now I can give a definition. A quandle. So is a set with an internal composition law. Such that I have three axioms. So the first one is that it distributes over itself. The second one is that this map should be a bijection from Q to Q. And the third one is that we should have idempotence. And so here we can remark that the first axiom says that these maps here should be endomorphisms. So Q acts on itself by endomorphisms. And in fact, the second one says that, in fact, these are automorphisms of Q. Automorphisms for the law itself. Okay, so now we can define, if I have L a link and Q some Quandle, I can color some diagram of L by elements of Q, and this will be the number of colorings of some fixed diagram of L by elements of Q, following the rules I have set. And these axioms are exactly what are required for this to be actually a link invariant. It doesn't depend on the choice of the diagram. Okay, some examples of this, where we can recover some usual stuff. So the first one will be a Quandle with 3 elements. And then I will require that one element has to ask by to act by permuting the other two. So beta sends alpha to gamma, and beta sends gamma to alpha, and then gamma sends alpha to beta, and gamma sends beta to alpha. And on themselves, there is the idempotence axiom to complete this picture. And so this is a Quandle law. You can, this is a Quandle. And then what are colorings by these? So let's say that A is yellow, B is red, and gamma is blue. Then colorings by Q have to look like this. Either you have only one color, and this is the idempotent law, and or you have 2 colors, and then since the action of the red will switch yellow and blue, you have to have the other color. So actually a coloring by this is a tri-coloring of the diagram. And you can say that a knot K is tri-colorable if and only if the number of colorings of K by Q is strictly bigger than 3. You have 3 trivial colorings by only one color. And then if you have one more, it has to have all the colors. So this is classically a proof. It allows us to prove that the trivial knot, which is not tri-colorable, obviously, is different from the trefoil knot, which has this obvious 3 coloring. not so obvious if I do it like this. So generalization of that to n colorings. You take Q, which is integers modulo n, and the law has to be symmetry with respect to I acts by symmetry with respect to I, which is this. And then colorings will be something where you get, if you have K and A, here you have K, A, J, you have K equals A plus J. Okay, other examples. Sorry? You don't have the coloring base. There is one color which is different. No, what I mean is this one, okay, this one is not isotopic to this one because here you have a non-trivial 3 coloring and here you don't. So here this number is bigger than 3 and here it's equal to 3. Yes? Yeah, I'm not quotienting by an action of the symmetric group or anything. Yeah, yeah. I mean, you could, but I'm not doing that. So let me give you some examples that are a bit different than the first two. So if X is a set, then X is actually a quandle for the law with every element acting trivially on all the others. And this is called a trivial quandle. If G is a group, then you can see it as a quandle for the law G acts on H by conjugation, like this. And actually, if there will be groups in what follows, they will always be endowed with this quandle law if I want to consider them as quandles. So another example from closer to knot theory is the fundamental quandle. And the idea is that basically you can look at the Wirtinger presentation of the fundamental group not as a presentation of a group, but as a presentation of a quandle, because the only thing you need is this law of conjugation. And so you choose a diagram of the link L. And then the presentation is as usual. So you take arcs of the diagram that we'll call D. And the relations are actually exactly what I drew up there, which is you have one relation like this if you have some crossing like this, and you have another relation, another family of relations like this for the this was already negative, so positive crossings. And this is you take this as a presentation of a quandle. It's the quotient of the free quandle on these by these relations, and you can do that. You have to trust me on this. And so if you do Reidemeister moves, you will get isomorphisms of this, and so this up to isomorphism depends only on the link. And also, it's kind of the universal quandle to color L. And so the by construction, you can interpret the colorings of L by some quandle Q. you can interpret it as the number of morphisms from the fundamental quandle of L to Q. Because taking such a morphism is choosing where you send the arcs, so one color for an arc, and they have to satisfy these relations, and these relations are exactly my rules for colorings. No. In general, quandles are not finite. This number is not necessarily finite. In the sequel, I will ask this one to be finite, and then it gives a numerical invariant. But in general, you can just say that. Okay, so now that I have defined them, I need to draw a big diagram. Do I have enough space here? Maybe. Okay. So let's begin. So this is part 2. I will talk about context. So I will begin with a link L. And the usual story, the kind of the historical story of the beginning of knot invariance is, okay, we will consider the complement which is S3 minus L. This is a 3-manifold. And if you get an isotopy of the link, you get a homeomorphism of the such manifolds. So this is a link invariant, and it keeps a lot of information. And then if you want to go algebraic, you will take the first algebraic thing you can think of, which is the fundamental group of this manifold. Which is called, say, could call it the link group. And then if you want to get numerical invariance from this, you can take the number of morphisms from this group to some finite group. So here you have some loss of information. So here you are losing some information, meaning that there are links that are different, but the complement is homomorphic. Here you have another loss of information. There are knots with a homomorphic complement and not the same group. The simplest example, I think, is the granny knot and the square knot. And here there is another loss of information. But in certain cases, and in particular for prime knots, it's conjectured that you're not losing so much information. And actually, so if you take only one invariant, of course, you're losing a lot of information. You get one number is clearly not enough. But if you consider this for all finite G's, then this is actually the same. You get exactly the same information as in the profinite completion of your group. So this requires a little bit of work. This is actually a paper by Dixon, Formanek, Poland, and Ribes from '81. But actually, this is one way to think if you don't want to think a lot about profinite completions, because they are kind of technical objects to deal with. You can think of them as having this same information. That is, it's a way to encode morphisms to finite groups. And here, this question of the loss of information is the big question of profinite rigidity. So if you take a group, you take its profinite completion, can you recover the group from it? That's the big question, and there are lots of things that we don't understand there. At least, yeah, we don't, and I understand less than what is understood. I think that's not only. The question is, can you recover GL from this? So can you characterize? Is it? So no, the question is, can you recover GL from the profinite completion? And if you know that it's injective and you can't characterize the image, then I guess the exactly up to continuous isomorphisms here, and up to. Yeah. It's true in some cases, it's false in others, and it's conjecture that, and it depends also on the family of groups that you consider. Among a family of groups, you can be rigid or not rigid in general, and there are many questions around this. But what I want to talk about now is Quandles. So, okay. The idea is we want to concentrate on the kind of difficult question, which is profinite rigidity, and maybe try to control this loss of information here. So one way to do that is, so here, if we want to control it, you can actually take more information into this algebraic invariant. So here, what I will do is take what are called peripheral subgroups. And so let me try to have some space here to define them. So if you can think of your complement here as actually you remove a tubular neighborhood of L. This is slightly different, but not that different. And the idea is that if you do that, the boundary of this becomes a manifold with boundary, and the boundary is actually a bunch of tori. One tori for each component of the link. You just remove a solid tori around around each component. So now what you can do is, if you take the pi1 of XL, inside there, you will have these pi1 of these tori, which are Z2, and the images of these morphisms, you have only one if you have a knot, several if you have a link. Images are called Pi. I is my index for the link components, and these are called peripheral subgroups. And actually, the big theorem by Waldhausen is saying that if you have the group with peripheral system, with the peripheral subgroups, sorry, then you can completely recover the manifold from there up to homeomorphism. So this part here is Waldhausen. So here we have still an algebraic invariant, but which is stronger, and the loss of information here is for getting these subgroups, which is a bit easier to understand. Okay, and we can actually do something better, which is inside there, you will add the data of up to conjugation of the meridian around the ith component of the link. So this is a bit more data. It's an element in Pi because the meridian is a loop around your component, and Pi is this fundamental group of a tube around your component. So there is a little more data here, and actually the construction by Joyce or by Matveev, but I will use the one from Joyce, is saying that this can be encoded in the fundamental quandle of the link. And here, the loss of information is can be controlled. That is, in fact, QL is isomorphic to QL prime. So for knots, I was saying up to mirror images. For links, it's a little bit complicated. It's up to taking a mirror image of a split component. What I mean by that is if I have a link that is let's say something like the well, trying to draw a threefold, but yep. If I have a link and I can draw spheres around a part of the link, then I can take the mirror image of just that and keep the other parts still. Okay. So actually here, if we have lost only the question of mirror images of split components, and so then if I want to do the same story as here but with this stronger invariant, I can actually do the same. I take the number of homeomorphisms from Q to a finite quandle. And as I just said, this is the number of colorings of L by Q. And actually, this is the same as what I will define in a moment, which is the profinite completion of the quandle. If I look at this for all finite quandles. Sorry? Okay, in general, the fact a quandle will not inject in a group, and for fundamental quandles, the fact that a quandle injects in a group is equivalent to the link being prime, so the being a knot and being prime. Or I think at least for knots, that's true. So no, I can't just restrict to subquandles of groups. So, okay, this will be the same as this, and for this, we will actually adapt So this is the first part of what I did, which is adapt this to the world of Quandles. And another part is to adapt the construction of Joyce. So I wanted another color. Adapt the construction of Joyce here to say that actually this is the same as some kind of profinite peripheral system where you really take the profinite completion of the group, and then you take the closure of the peripheral subgroups in it, and then you take the image of the meridians in there. And this is actually an adaptation in the profinite world of the construction of Joyce. So. And you can see that all this sits above what is there. So here, if you look at actually, if you look at these, you can recover morphism to a finite group of your fundamental group, because your fundamental group is defined as with the same presentation as the fundamental Quandle. So if you have a morphism to a finite Quandle, you will you can take the group, a group associated, I will not explain the construction, but a group associated to this one, which will take it to a finite group, and then you will get that. And the obvious, so this is not actually kind of not obvious, but the obvious thing is that you can recover the profinite completion from this, because it's in there. Okay, so yeah, I was coming to that. So here I have basically no loss of information. I mean, up to mirror images, a split component is okay. Here, the question would be, do I have loss of information to these? And the question of loss of information here is a question of profinite rigidity. And actually, it was conjectured, at least in the world of Quandles, that there was no loss of information. And let me write, I will write down the conjecture now. So the conjecture, which is in the world of Quandles, so you can quote Clark, Saito, Carter, etc., is that for all Q finite Quandles, if I have for all finite Quandles, so L and L prime links, if the number of colorings by every finite Quandle is the same, then this is equivalent to this. So this conjecture is exactly saying, okay, there should not be loss of information on the top maps here. And actually, my work is kind of trying to reformulate this in words that are closer to the world of profinite rigidity. And in particular, this is related, there is a conjecture in the world of profinite rigidity, which is that if K is a prime knot, K and K, let's say K and K prime are prime knots, then isomorphism between these profinite completion, then K should be the same as K prime up to mirror image. So these are two well-known conjectures, and the goal is kind of to reformulate this one in words closer to that one. And actually, this hypothesis here, as I was saying just before, the fact that a knot is prime is exactly when its fundamental quandle will inject in its fundamental group. So probably the one we get about rigidity actually of profinite peripheral systems should be better, should be a good place to insert this conjecture. Okay, so let me actually talk a bit now that I have explained the context about profinite completions and actually what I did with these this stuff. Are there questions so far? Yes, this is my notation for the number of colorings by, of L by Q. Okay, so actually what I'm going to, oh, okay, I still have this I want to say. So actually what I'm going to focus on is the first part of the, up here, which is this adaptation of the world, the work of Dixon, Formanek, Poland, and Ribes to the world of Quandles. And the first thing I have to do is to explain a bit of interactions between the Quandle theory and group theory. And for that, I have to speak a bit about inner automorphisms. So if Q is a Quandle, the inner automorphism group of Q will be the subgroup of automorphisms generated by the automorphisms coming from elements of Q. And one important thing in Quandle theory is that understanding the inner automorphism is kind of an essential part of trying to understand the Quandle. So you can do group theory and get results on the Quandle. And so maybe some mark first. You get a map from Q to the inner automorphism group, sending Q to the associated automorphism. And this map is actually a Quandle morphism. So this is a Quandle because this is a group and you take the conjugation law on it. And this is a Quandle by definition. And this is actually very easy to see. That is, if you take this image, then this is taking the associated automorphism, and then this is the same as this. Why is that? That's because here you can distribute this one over these two and get back first one. And this is actually exactly what we want, which is the conjugation in the group. Okay, and what I was saying about group theory interacting with Quandles theory, I will illustrate it with this lemma. If Q is a finitely generated Quandle, and if the inner automorphism group is finite, then Q is finite. This is actually easy to prove, but I don't think I will have time to do the proof, so I will get to speaking about Profinite completions. So I led the proof of this lemma as an exercise. And if I want to talk about profinite completions, I first have to talk about how to deal with finite quotients in an efficient way. And to deal with quotients, for groups, you deal with quotients by normal subgroups. So a normal subgroup is something around the identity, and why we deal with normal subgroups is because groups are homogeneous. But for Quandles, you don't have this kind of homogeneity. So you really have to consider equivalence relations. And if R is an equivalence relation, saying that to have all so the compatibility you need with the Quandles law is the first one you can think of, actually. R is a congruence if and only if for all in Q. If I have x which is in relation with x prime and y which is in relation with a y prime, then x, y is in relation with x prime, y prime, plus the same with the inverse law. So that's actually the second you can think of, because the first one is this one. The second is with this other condition. And the idea is exactly that if R is a congruence, then Q over R will be a Quandle, and the law will be what you expect, which is if you take the class of an element X and the class of an element Y, then you can just take the class of X acting over Y. Okay, and the other thing is that every surjection, that is every surjective morphism, is the quotient by a congruence, which you can think of as the kernel of P, which would be the kernel of P in group theory. And this congruence is just the one given by X is equivalent to Y if and only if they are sent to the same element in the quotient. Of course, up to isomorphism. Okay, let me give you two other facts about congruences, and then I'll talk a bit about profinite completions. If Q, X, Y are elements of Q, and there is some congruence R on Q, and we have that, then we obviously have that because of the definition of a congruence. But why am I writing that? That's because then this implies that this map here passes to the quotient. And actually what you get from that is a surjective morphism from the inner automorphism of Q to the inner automorphism of the quotient, sending this map to this. And so we want to deal with profinite completions. So definition: Q is a Quandle, R still a congruence. Then R is of finite index if the quotient is finite. And the order of the quotient denoted like this we call the index. Okay, I have, I think, 8 minutes left to talk about a little bit about the profinite completion. Okay, so the profinite completion is defined as usual. That you take all of the finite quotients. So this means that you take all congruences of finite index. And you take the projective limits of all of this. So if you're not completely familiar with it, I will tell you a bit more about it. So it sits inside the product. It consists of coherent families. So you take one element in each finite quotient, and if you project further to another quotient, then you get the element in the another element of the family. And here you have a topology, which is the product topology. All of these are finite, and I consider them discrete. And then you get a topology on this space. This is the profinite completion. And so let me state the theorem. Which is not yet on the archive, but soon, hopefully. If Q and Q prime are finitely generated quandles, the following are equivalent. The first one is that if X is a finite quandle, then the number of morphisms from Q to X is the same as the number of morphism from Q prime to X. 2, if X is a finite quandle, then X is a quotient of Q if and only if it is a quotient of Q prime. And the third one is that there is a continuous isomorphism between the profinite completions. Sorry. And this does exactly what we wanted here, which is to relate this statement, to relate this families of integers, this family of integers to the profinite completion. Okay, so here are a few things. Let me say a few words about the proof. Actually, there are beautiful ideas in there. Not mine for the most part. So the first obvious thing is that we have this, and this is actually by construction. By construction because actually to have morphisms from Q to a finite X is exactly the same as to have a continuous morphism from the profinite completion of Q to X. So if I know profinite completions, I know these numbers. This is by construction. So the second, which is not very difficult, but the proof is quite beautiful, is from here to there. So you actually know number of morphisms, but here you want to know surjections. And so what you want to do is you want to count them, so X finite. If X is finite, you have a finite list of proper subquandles. And if you want to count surjections from Q to X, then you first count the number of morphisms. Then you want to remove non-surjective ones, but a non-surjective one is one going to a proper subquandle. So you remove the sum of the number of morphisms from Q to each xi, but then you have counted too much, and this goes to, you want to add once the one coming from intersection of two of them, and then you have a usual inclusion-exclusion formula. And so if you know the number of morphisms, you know the number of surjections, and you can decide if there is one or not. So that's one implies two. And the last one, I will finish maybe by a little statement. So the last one is actually the difficult part. The reason is that you know which elements are quotients of, which finite quandles are quotients of Q, but this is this kind of discrete data. You don't have the morphisms that are in your projective system that you want to rebuild this. And so you have to be a bit clever to go from this discrete data to this kind of coherent data about quotients, about finite quotients. And so you can adapt completely this work of, let me write their names, Dixon, Formanek, Polland, and Ribes. The thing is, it's actually very general. They do it for group theory, but you can do it for every kind of algebra. With one condition, you need to have this theorem, which is that if you have a finitely generated quandle and you have n an integer, there exists a finite number of congruences on Q such that of index, there are of index n. Probably know this from group theory. And this is the crucial part. It uses this lemma that I left as an aside here. And you cannot directly adapt the proof for groups. All the rest works exactly like there. I don't think I have time to tell you how that goes, so I will stop here.